Alright guys, today let me explain how methionine is converted to homocysteine and what will happen to homocysteine in our body. So what is the fate of homocysteine and all that, and what are the different vitamins that are required for conversion of homocysteine into cysteine or into methionine. So let's start with methionine first. So methionine is an essential amino acid. As you all know, we remember essential amino acids with private timhal, and within that private timhal we have methionine. So we consume methionine, and methionine will undergo metabolism within our body. So it will become part of a polypeptide chain, and also it will undergo other metabolic fates. One of the metabolic fate of methionine is converted to S-adenosyl methionine, and S-adenosyl methionine is participating in methylation reaction where methyl group is donated, and once the methyl group is donated, S-adenosyl methionine is converted to S-adenosyl homocysteine. Now the S-adenosyl homocysteine will be converted into homocysteine once the adenosyl group is taken out. Now the homocysteine here, it has got two fate. If the intake of methionine or if the demand for methionine in the cell is more, homocysteine can be converted into methionine. Or if the demand for cysteine in the body is more, if our cells need more cysteine, so homocysteine can be converted into cysteine. So going towards the cysteine formation, homocysteine is initially converted into cystathionine, and this cystathionine further down is converted to cysteine, and cysteine is an amino acid. That is why, so basically cysteine is a non-essential amino acid. Why? Because methionine is an essential amino acid. As long as you consume methionine in the diet, it means you can synthesize cysteine in our body. That is why cysteine is not essential in the diet. Okay, let's move on to see how homocysteine is converted to cysteine first, and then I'll explain you how homocysteine is going back into methionine. So homocysteine into cysteine formation, we need an enzyme called cystathionine beta synthase. Cystathionine beta synthase. This cystathionine beta synthase enzyme, it needs a coenzyme. And that coenzyme for that is pyridoxal phosphate, PLP. PLP is an active form of vitamin B6. As you all know, pyridoxine, active form of pyridoxal phosphate. Cystathionine beta synthase coenzyme is pyridoxal phosphate. So if there is sufficient availability of pyridoxal phosphate and cystathionine beta synthase working, so homocysteine can be converted into cystathionine. Now the cystathionine can be converted into cysteine by cystathionase enzyme. Cystathionase enzyme. This enzyme also needs pyridoxal phosphate. Cystathionase enzyme also needs PLP, vitamin B6 derivative. That's how you make cysteine. Now what happens is, if there is a mutation in an enzyme which is in a gene coding for cystathionine beta synthase, if this cystathionine beta synthase is not formed properly, if this is a mutant enzyme, so its activity decreases. Or if there is a deficiency of pyridoxal phosphate in a body, in the food or in a person, so when the pyridoxal phosphate is down, cystathionine beta synthase will also decrease its activity. So during that time, what happens? There will be increase in homocysteine levels, and that is called as homocysteinemia. It will lead to homocysteinemia, excess levels of homocysteine in the blood. Later it appears in the urine, and that is called as homocysteinuria. So there are two conditions. That means one condition, the two terminologies there. One is homocysteinemia, other is homocysteinuria. Homocysteinemia. Homocysteinemia means excess homocysteine in the blood. Homocysteinuria. Homocysteinuria means excess cysteine in the urine. So whenever it is excess in the blood, it will appear in the urine. So both the terminologies we use interchangeably, but the disease is same. Now that's how homocysteine is converted to cysteine using these two enzymes and the coenzyme. Now let's move on to see how exactly homocysteine is converted to methionine. That is done by an enzyme called methionine synthase. Methionine synthase. And this methionine synthase, to convert homocysteine into methionine, it needs a coenzyme for that. And the coenzyme for methionine synthase is methyl cobalamin. Methyl cobalamin, I'll write it as CH3B12. This is a form of cobalamin. We have two forms of cobalamin. One is methyl cobalamin, which is needed by methionine synthase. Other is deoxyadenosyl cobalamin, which is needed by methyl malonyl CoA mutase. That we'll see later. Some other time I'll make a video on that. So methyl cobalamin gets into the reaction used by methionine synthase, and it is coming out of the reaction as just cobalamin B12. Now these coenzymes need to be regenerated in our body, reutilized, so it has to be converted back into methyl cobalamin, and that job is done by one more reaction. So we use N5 methyl, I'll write it as CH3, N5CH3 THF, that is tetrahydrofolate. N5 methyl tetrahydrofolate will give that methyl group to B12, and that's when B12 is converted to methyl B12. So N5 methyl tetrahydrofolate means N5CH3 THF is coming out of this reaction as just THF. So I can connect the reactions together now. So it will be something like this. B12 takes methyl group from N5 methyl tetrahydrofolate. That's how you are regenerating methyl cobalamin. And your N5 methyl tetrahydrofolate is coming out as tetrahydrofolate. As you all know that N5 methyl tetrahydrofolate, this is the major storage form of tetrahydrofolate. It's a circulating form of tetrahydrofolate. So this reaction has to go on well in our body so that you can convert tetrahydrofolate. You can free tetrahydrofolate from N5 methyl tetrahydrofolate. So this is the reaction which will convert N5 methyl tetrahydrofolate into tetrahydrofolate, and this tetrahydrofolate can get into other tetrahydrofolate derivative formation. It can be N10 formyl tetrahydrofolate. It can be N5, N10 methylene tetrahydrofolate, or any other derivatives. It can be N5 formyl tetrahydrofolate. So for all those derivatives, you need tetrahydrofolate. Okay. So this is the reaction which is going to free tetrahydrofolate from N5 methyl tetrahydrofolate. Now, what happens if there is a deficiency of cobalamin? Consider that there is deficiency of vitamin B12. B12 is down, deficient. When there is a deficiency of vitamin B12, so the reaction which is using the N5 methyl tetrahydrofolate and releasing tetrahydrofolate, that reaction decreases. So this particular reaction will decrease. So this will lead to accumulation of tetrahydrofolate as N5 methyl tetrahydrofolate, and overall there will be decrease in tetrahydrofolate. Because tetrahydrofolate is decreased, that will decrease other derivatives of tetrahydrofolate. So that's how metabolic reactions are affected. It means there is a tetrahydrofolate, but effectively it is not available to make other tetrahydrofolate derivatives. This will lead to functional folate deficiency. Functional folate deficiency means you have folate here, but all the folate that you have in the body, most of the folate, not all, most of the folate that you have in the body is in the form of N5 methyl tetrahydrofolate. So because there is vitamin B12 deficiency, this N5 methyl tetrahydrofolate is trapped here. It is not converted to tetrahydrofolate. So this is called as functional folate deficiency. This entire concept, we call it as folate trap. This is the concept called folate trap, and this folate trap is because of cobalamin deficiency. Okay, so if everything is fine, if the normal cobalamin is available, normal amount of tetrahydrofolate available, so at that time homocysteine, and if methionine synthase is fine, so at that time homocysteine is converted to methionine. If just in case, if there is a deficiency of methionine synthase or a mutation in methionine synthase, or if there is decrease in vitamin B12, or if there is decrease in tetrahydrofolate, so there is increase in homocysteine, because homocysteine won't be converted to methionine. So there are three vitamins in our body which can lead to increase in homocysteine level. Increase in homocysteine means which will lead to homocysteinemia, and those vitamins are vitamin B6, that is pyridoxal phosphate, then vitamin B12 deficiency can lead to homocysteinemia, and folate deficiency. Folate deficiency. All these deficiencies, folate deficiency. So deficiency of vitamin B6, deficiency of cobalamin, deficiency of folate, all of them, they can lead to homocysteinemia, later into homocysteinuria, and that you can understand by this particular pathway. Thank you.